Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So what I'm going to do in this talk is just basically go over 5 directions that interest me for my recent research, and hopefully try to, by doing this, establish connections with folks here in Cambridge, and and embark on cool joint projects together. So the 5 directions that I'll talk about today are the ones that we have over here. The first one is of a theoretical nature, and it's about random forests. I think Microsoft Research is doing the coolest work that there is out there in random forests. And I've been a huge fan of the work of Jamie Shotton and Antonio. And they've produced this great work and great books that even my undergrads love to read and understand and implement. And so at the practical frontier, they've really made great leaps and bounds. And what we've been trying to do is work on the theory, because to this day, the original algorithm of Bryman remains not proven to be correct. I'll say more about that. I'll talk about de-randomization of algorithms. There is how you take a stochastic algorithm and make it deterministic, and why would you want to ever do that? I'll talk about probabilistic graphical models, which is also an area that I think there's been a lot of good work here, especially with infer.net and so on. And I'm going to talk about the problem learning there, and something that's sort of hot and new in the sense that I submitted this paper at midnight last night to ICML. And how to, for some models, be able to make learning linear in the size of the graph as exponential in the size of the graph. Then I'll mention briefly some deep learning, and then I'll talk a bit about Bayesian bandits and optimization, a topic that I'm super interested in. So here's some motivation for the work. So assume that, and you've seen plenty of motivation for random forests, but I'm going to give you an alternative motivating take. Suppose you wanted to build a digital magazine. That is, you open your iPad, and every day you have your magazine on any topic of your interest. Like you could have the Bayesian magazine in this case, that's the title of the magazine. And every morning you get interesting articles, like Andrew Gellman's blog, Christian Robert's blog, and so on. So it's a sort of cool, easy read articles about machine learning, not necessarily, sort of a JMLR paper. And you might want to have a magazine for many other topics of interest, Bayesian or neural networks or Oxford or statistics, or these are some of the things that interest me as topics to read. But in order to have such a magazine, you need to scout the whole web for the interesting articles to be able to deliver to each user. You need to personalize to each user, and if you want to succeed, you probably will have, you would hope to get at least over 1 million users. You need to know what article is about what topic. So in a sense, you need to classify any new article that is of interest into a particular topic. Now imagine that, so you could use a resource like Twitter, for example, to tell you what's exciting out there in terms of articles, or what's trending, something that captures the zeitgeist. But then you would have to grab that article and say, what are the topics that article is about? So here's one way you could do that. And by the way, this digital magazine is actually a real thing. I built it with my students. It's called Zeit, and CNN acquired us, and it now powers CNN. And this is how we go on about tagging. So the problem with tagging is this, that most of the web doesn't have labels. We want to be able to classify web pages, but if you just rely on this, what folks have done in terms of building ontologies and so on, there's very little you can do. So what we did was, over several years, we crawled Delicious. This is being recorded, right? Anyway, we did get Delicious. Then no one stopped us from getting it. And Delicious, I believe now, belongs to Google. It used to belong to Yahoo. It was one of those products acquired by Yahoo that did not evolve. And what we did was we crawled about 100 million pages. There's a one factor higher than, actually almost 2 factors higher than Wikipedia English. And we used the labels that the users provide us to essentially build classifiers. And the way we build those classifiers is we do extract the text out of an article. We also extract the text from the articles that point to it. So we get a context. We produce thousands of features for the document. And then from those thousands of features, we use a classifier. What could you use here to classify the web? Random forests. And that brings us to this issue that despite the fact that random forest is so useful in medical imaging, in computer vision, and that is like one of the best classifiers out there, it's obviously scalable. We were using it to tag 1 billion documents. It has this problem that for an academic that is sort of not satisfying, that is it's never been shown that it actually gives the right answers. So if you have some measure of cost or performance, it's never been shown that as the number of data grows to infinity, that cost will go to 0. Never mind getting convergence rates. It's just that very basic, does this actually work as I keep getting more data? So I'm going to take you over an example. In this case, I'll focus on regression. And I know that this is sort of a powerhouse on random forests. If you haven't seen random forests before, I apologize. For this part of the talk, I will assume that you do know random forests. If not, go and bug Antonio for a copy of his book. But so very quickly, for those of you who already know random forests, what you do there is you build trees that split the space. And then on each leaf of the tree, you fit just in this case, we're doing random forest for regression, so we just say fit a line. So you do a piecewise approximation to your data if you're doing regression. And typically, the way you do that is you construct predictors for each leaf, and you construct many of these trees, capital M of them, and then you average these trees, and this gives you the strong classifier. So each of these guys corresponds to the classifier for the tree, and then you combine them to produce the forest. So it's actually extremely easy to implement. As to construct the trees, we often use heuristics. Like in this case, the heuristic that's being used is that if we're trying to minimize the squared error between the fit, any point in the mean, then we just need to make sure that we try to minimize to maximize information gain, or in this case, error reduction. Another thing that we do, and some folks don't actually go over this exercise of doing some optimization to do the split. Some folks just do this randomly. They just pick some point at random, and then they split, and then just construct these trees at random. And I'm going to show you a few examples of what you get and miss by doing that. Another thing that I'm going to do to show you the sort of results we can get is I'm going to assume that if I have, say, these features in a million dimensions or so, and I'm going to take a subset of them, I'm going to pick a few of the dimensions, and then I will project my data, a subset of my data points into those dimensions. And you can think of this as the projection into one of the dimensions. And for a subset of the points, then I'm going to do a search along the solid line while computing this objective, and then pick the optimal split point. I'm going to do the following thing that is essentially in order to get a theory, and this is the sort of the key trick that has allowed my students and I to get what I believe are the best bounds right now for, or at least a theoretical random forest, the closest match of what exists in practice. We split the data into two streams. So when a point comes, each tree separately flips a coin and decides whether that point is going to be used to decide how it builds its structure of the tree, or to do the estimation of the leaves, to sort of fit the line. Okay, so we're separating estimation from structure building. And a point that is used for structure in one tree can be used for estimation in the other tree. So that's also sort of important. So we're trying to maximize this. Then what does it mean for something to be consistent? It means that you minimize some error. So if this is the optimal function, then what we're saying is for any x, so we're going to do this for any x, if you have a classifier that depends on your data set, it has some sort of randomization due to all the different randomization you could inject in the algorithm. And also for any input, you want this error to go down to 0 when you do regression, so that you can approximate the conditional mean. How do we prove that this risk goes to 0? I'm just going to quickly, in 3 slides, go over the main ingredients in a proof of random forests. The first thing is to appeal to a theorem that actually turns out to be only require about 2 lines to prove. And what that theorem says is that if your basic weak learner is consistent, if your tree is consistent, then the forest is consistent. When I first saw this theorem, I thought, oh, it's going to be so easy to prove results for all sorts of random forests. And then I realized no one had ever proved consistency for a tree. So decision trees, that's even more shocking. Decision trees have existed for such a long time, and no one's ever bothered to actually show that they're consistent. Now, when we do the other thing that we need to prove is that if we separate structure from estimation, if we're creating 2 streams, and we have this conditional risk, we want to show that but if the conditional risk goes to 0, then our original risk also goes to 0. This is very easy to prove. It's, again, about 3 lines, and I can go over these proofs with you later. And that's just an exercise of you build a joint, you take a double expectation, you use the fact we put assumptions to make sure that these guys are bounded. We use dominated convergence, it's a classical limit to swap limits with integrals, and that's it. That's the proof. What it gets interesting is the last step of proving one of these results. So for the single tree, now we know we separate the structure from estimation. And for a single tree, in order to prove consistency, we can resort to a huge literature that is out there on consistency of nearest neighbor classifiers. In particular, if you think of classifiers and regression functions as well, the intuition here is that each leaf is essentially a neighborhood. As you're splitting the space, you're just creating these neighborhoods. Now, what you would want, if you wanted to get a perfect fit to the function, is that you would want these neighborhoods to shrink to 0. Okay, so if we have any leaf, so I'm going to have this condition that the diameter, which is a measure of the size of the leaf, must go to 0. I also want that as the size goes to 0, that the number of points still is large enough that I can get a very good fit. So I need a number of estimation points to go to infinity. Now, in order to establish these conditions, all we have to do is say that a leaf will not split until a particular parameter of the algorithm, Kn, until there are that many points, until there are Kn points in that leaf, we want split. This is sort of already proven, because just by having this condition and letting this parameter grow with the data, then we achieve this result. So in effect, we only have to prove this, that the diameter shrinks. To prove that the diameter shrinks, the whole space shrinks, you only need to prove that one of the dimensions shrink. That's 2 pages of analysis, which I'm not going to bore you with. But it's becoming kind of standard, because there is a sort of a general formula for doing this, and then whenever we get a new algorithm, we just need to rework the proof a bit to be able to get this sort of thing. So at the theoretical front, thanks to tools developed by Jorfi and de Vrooij and Lagasse, we're able to actually now do this. But the key trick is that all these theorems from this literature rely on the fact that the structure has to be independent of the estimation. And by doing the splitting of the streams, we can reuse some of the ideas there. Now, what are the, how does this manifest in practice? So here there are 3, in red, green, and yellow, there's 3 theoretical random forest algorithms. So by theoretical random forest, I mean random forest algorithms for which we can prove consistency. And the one at the bottom here is Bryman's. Now, Bryman's still does better than any of the methods that we have. The goal has been to narrow this gap. And so Gérard Biao and Luc de Vrooij, and I think Gabor Lugos was part of this too, they proved this first result, which they published in JMLR. More recently, Biao was able to come closer. We're currently sitting here, but I think we're getting very close to prove, to have theory for something that's very close to what's used in practice.
Is this process theoretical bound, or is this the simulation results?
These are simulation results. So that's with some UCI data, one UCI data set. Here there's another. We've done this for many UCI data sets, always observed the same thing, where the sort of Brymans are down here, ours are here, and then the Biao, which are the other best results out there, are up here. And so we observed that for another data set.
And the key algorithmic difference is the dual stream sort of aspect of it?
And so we've been studying how much difference is the 2 streaming causing, how far is it separating us. It turns out that we then have been trying different permutations. What if we took Brymans with the exact same split? Because all of these have also slightly different splitting strategies. And so we've been sort of playing a bit. And in fact, there's some versions here. And this might change because my students are working on this as we speak. They're trying to get this particular version to similar. There's some particular versions where if we start introducing our ideas from splitting that we sort of came up with following the theory, we start doing better than the Bryman. But for that one, we have no theory.
In the original Bryman algorithm, we did bootstrap resampling. Why you haven't mentioned that? That's quite essential in practice as well. At least it makes big differences.
Yeah, it's essential. There's a whole story that comes in with that kind of randomness, which I've obviated. We do a form of bootstrapping as well, because in our splitting mechanism, we only use a subset of the points. So we're doing some form of sub-bagging. But we haven't actually... so we do have a form of sub-bagging, but Bryman does actually do the bootstrap, and he doesn't sub-bootstrap. He actually uses the whole thing. Antonio has this beautiful picture in his book where he shows that the advantage of that is that if you have outliers, you can be a bit more robust. You don't get a max margin classifier, but you become robust to outliers. So bootstrapping can help you in those situations. For our particular way of doing things, it will not necessarily help us with if there are outliers. So if we introduce a data set with outliers, I think the difference is going to be even bigger.
But the results you show is with bootstrap resampling.
Without.
Say Breimann is with bagging or not?
Did measure run bootstrap? I believe so.
Can you remind me what Breimann suggests for the number of trees you're using, and also how your theory relates to
Right,
the
so
number of
we've tried to use the same, we kind of actually show here that essentially more trees is what you should be doing. This is as you increase the number of trees.
Is there a scaling law that Breimann suggests? Or I imagine it might depend not so much on the data, but on the complexity of the regression surface.
You basically use as many trees as you can afford, and you stop when the results don't. He does make lots of suggestions, which in our experiments we've been trying to follow as much as possible. And of course, here is the sort of can't come here without this application. We've also been running this very recently on trying to predict joint locations given the class labels. And there essentially we see that for this application, Biao and 2012 and ours are pretty much the same. We still sort of age it a little bit. And again, the original Breimann version of random forest is still better. Again, the goal has not been to outperform Breimann. The goal here is how can we narrow the gap between the theory and the practice? There is this algorithm out there that is extremely hot, that is extremely simple too, that everyone uses, for which we have no theory. Can we at least come closer to that algorithm and eventually get something that performs just as well and for which we can develop the theory? We're still not yet there, but I think we've taken steps to do that. And then one thing we've been able to do, where I think we start departing from the state of what exists, is for online random forest has never been approved either. And so we've actually been able to use the same sort of ideas with a few complications that have to do with how online trees have to keep statistics in order to decide where to grow or to stop growing. But if we have streaming data, we can still get the same type of convergence consistency now. And they're the type of things we had to do in the theory. Unfortunately, I was on the train and I still don't have wireless, so I couldn't put a picture here which was going to show that we beat the state of the art in terms of algorithms. So I'll just tell you, we do beat the state of the art. And so it was one of those cases where by actually considering the guidelines of the theory, we were able to create an online random forest that is better than any other online random forest we know of. Okay, so that's essentially where we are with random forests. And obviously, there's lots of things to do still. I think we would love to get finite time concentration bounds. And I think some of the things we've done hopefully laid some foundation toward getting that. We would like to then attack all these more complex models that Jamie and Antonio and a few others have been developing. And so I think there's a lot of cool work happening now at this interface between theory and practice in random forests. And I think we're coming closer. So very quickly, another topic that I've been working on with that I will planning to continue working on. And this I don't know to what extent folks here will be interested in, but I did want to explore it because I think it's a fascinating thing. So Max Welling came up with this algorithm called herding. What herding is basically a two-step greedy algorithm where if you want to, suppose you have some statistic mu and you want to approximate it by taking samples. So you have some sample statistic, you do like an ergodic average, and you want to approximate it. So mu could be a histogram, and these could be just indicators of which bin you fall in, and then you're using this empirical histogram to approximate this multinomial distribution. The algorithm is greedy. You don't need to know the horizon. And it just basically involves a dot product. and then something that looks very much like a non-line gradient descent where the step size is 1. So you're trying to match the statistics, and the algorithm has some parameters, W. It's completely greedy, and the reason why we like that algorithm is because if you're approximating this, the convergence rate of this algorithm is 1/t, as opposed to a Monte Carlo algorithm that would have a convergence rate of 1/√t. So it's quite an improvement, and you can see it in practice. So here for a model with 2 variables, I've run the stochastic algorithm, which is in blue, which is a Gibbs sampler, and then in red, it's an extension of herding to MCMC algorithms, which we call the herded Gibbs, and it converges much faster. And for some examples, like image denoising, it again outperforms Gibbs. It does as well as another deterministic friend, a mean field, except that mean field has a few free parameters. And if you don't know how to tune those, you can't match the performance of Gibbs herding. And the application we were really interested with that we think it's sort of this would be the sort of the killer application for an algorithm like this is named entity recognition with, or coreference resolution with CRFs. So in CRFs, for named entity recognition, sometimes it's important to have these edges that create that model long dependencies. If you're doing coreference resolution, that is, you want to know, I don't know, Obama does not like the Republican Party. He said that, so you need to know that he is referring to Obama, and so you need these long dependencies. And that causes trouble for algorithms like Viterbi and so on. And the Stanford named entity recognize implements something called annealed Gibbs to be able to solve this problem. So we just took their recognize and we replaced the annealed Gibbs by herding. And then what we find is that in the error for the deterministic version is, or in this case actually precision, is higher than the precision of the annealed Gibbs, which is the state of the art, in half the time. So it's a much more efficient algorithm. So this is exciting because we can go from a stochastic algorithm to a deterministic algorithm, get an algorithm that converges much faster. And Yu-Chien Chen proved that this was able to actually prove the theoretical rate of convergence. Yu-Chien is now working with Zubin. One challenge, like how can we keep extending these results? And there were some limitations with this theoretical result. And it would be interesting this would allow us to move, to sort of push the frontier of what graphical models we can do inference efficiently. Eventually, there are limits. So there's theoretical bounds on what you can do with deterministic algorithms versus randomized. If you want to compute the volume of a convex body in high dimensions, then provably there is no deterministic algorithm capable of approximating that. Whereas there is a stochastic one that can do it in polynomial time. But so there's a sort of very interesting interplay between randomizing algorithms and de-randomizing. When should you randomize? When should you de-randomize? And that's sort of, I think, a fascinating area of research. Another problem that arises with graphical models is learning the parameters, not just doing inference, but in order to create those CRFs, I also have to learn the parameters of the potential so that I can do all these sort of natural language processing applications and vision applications and so on. Now, there's many CRFs, many type of Markov random fields out there that people use. The physicists love these Ising models. Neuroscientists use them too. Gaussian graphical models are used a lot in epidemiology. Log linear models are classical models in statistics. And now in machine learning, these sort of conditional log linear models or conditional random fields have become very popular in a multitude of applications, ranging from biology to language to vision and so typically what we would like to do to learn the parameters is to maximize the log likelihood. Now, the problem with these models is that when you write down the log likelihood, the log of the normalizing constant, which is intractable, requires an exponential sum in order to get it, appears in the likelihood. So we can't evaluate the likelihood. And moreover, if you want to do gradient descent to optimize this, the gradient also depends on the log of this intractable normalizing constant. So we need to be able to approximate this expectation. Now, there are some cases where you can do this expectation. So if you have a chain, an HMM or a Kalman filter in the Gaussian case, you can do this. If you have a tree, you can do this. And in fact, if you have a generalization of trees, which is graphs with what this concept called log tree width, you're able to actually do approximate this with something called the junction tree algorithm. We decided to attack models of this structure, grids. Now, for a grid, if you look at the tree width of a grid with that is k by k nodes, the tree width is k. So the fastest exact algorithms that we have are exponential in tree width, and so their cost would be 2 to the k. So and I'm after exact inference here. I no longer want to do approximations. So with the best that we have now, inference is 2 to the k. And I'm going to show you a trick that allows you to do the inference in k.
But inference in planar graphs.
So sorry, learning. Go ahead.
Yeah, but inference in planar graphs is basically tractable in certain cases.
In certain cases, that's true. It's not always. So basically, you do reductions to SAT, and 2 SAT is tractable, max SAT is intractable for the general potential cases. And then anything above 3 SAT is intractable.
But I was thinking about restricted topology in the sense of a planar graph. So people have shown that you can compute marginals in planar graphs in certain cases in Ising models.
Very restricted cases. So for example, if you have the potentials all being positive, you can do that. For the general case, for example, if you want to find a map estimate of this, and then you don't have, and you have positive and negative, I think there's also there's one sub case there where you can do something good with mean field, but in general, in that case, that maps to max 2 SAT, and max 2 SAT is NP hard. So in the worst case, inference in these models is NP hard. And I'm going to show you soon this. I'm going to give you the lattice as an example, but soon I'm going to move to more interesting models, for which I will still make the claim that it's linear. Let's assume that this is not one of the trivial models that you could use and do exact inference, so that these are arbitrary potentials, for example, and that they're not necessarily Gaussian and they're positive and negative. So you have a frustrated system. So even with a simple cycle, you already would get yourself in trouble because it would be frustrated. Now, what we're going to do essentially, so why does the junction tree work? The junction tree, which is the sort of the most popular method for inference, it attacks an NP-hard problem, but it introduces a new concept called tree width. And then inference becomes exponential in the tree width, as opposed to exponential in the size of the model. So if we could come up with a different concept other than tree width, where the algorithm would still be exponential in that, but that other concept happens to have a size that is lower than tree width, then we will be able to have a new class of problems that we can attack efficiently. And so the concept that I'm going to introduce is the one neighborhood. So what's a one neighborhood? A one neighborhood is the union of all the variables that are involved in a clique that I'm trying to estimate and the neighbors of the clique. Or imagine that the clique of interest is the clique 7, 8 that I'm trying to, whose parameters I'm trying to estimate. So it's shown here in green. The one neighborhood then will be essentially the variables that intersect, that the clicks, whose clicks intersect with this. So 4, 7, 5, 8, and 9, 8. So in other words, these variables here. I'm also going to define the clicks involved in this neighborhood and call them F. So the clicks 4, 5, and so on. There are some other clicks that arise due to marginalization. Now, assume that you're trying to compute the marginal on the one neighborhood. You do that by integrating over all the variables other than the variables involved in the one neighborhood. Now, this marginal has a particular form. It has as factors the potential of interest, the other solid edges in the picture that I just showed, these solid edges, and a term that does not depend on the potential of interest. And that's going to be sort of the critical thing. The guy that interests me appears by itself. Moreover, when you try to prove that the exponential representation of a graphical model and the Markov representation of a graphical model, sort of global and local views of the same model. When you do the mapping by something called the Hammersley-Clifford theorem, as part of the proof, you need to construct these Mobius transforms and so on. And then one of the things that comes up is this question of uniqueness. Of uniqueness and existence of potentials. So it turns out that there is one particular type of parameterization of the potential called the normalized or canonical potential. And it's essentially, you could normalize it to any value, but you could just normalize it by saying the potential will be 0 whenever one of the variables in the potential is 0. And it's very easy to construct this, and Ising models will already be in this form. If you write the potentials for your model in that form, then this guy is unique. And because this guy is unique, and it appears as a factor here, and it appears as a factor in the original model, we can essentially just consider the variables in this one neighborhood, AQ. So if you have a big table of data, instead of considering all the million variables that you might be trying to analyze, you just need to pick the subset of the variables that you care about that are in this one neighborhood for the click, and you do maximum likelihood there. And that's the algorithm. So all you have to prove is that x of AQ is a sufficient statistic for the parameter of that potential. And then we do that. So basically, and this is sort of an example of this. So basically, the algorithm is you construct the one neighborhoods for each potential. You do it separately, so the algorithm is parallel. You construct an auxiliary MRF. By that, I mean just that collapse that marginal. You need to know something about the structure of the marginal. And then you basically just do maximum likelihood on the reduced set, and then you just read off the potential. And then this theorem here, for those of you who have the patience to read it quickly, is basically saying that that one neighborhood is a sufficient statistic. And so now if you have models like these, so it then becomes interesting to know when is this a sensible idea. If you have a restricted Boltzmann machine, this sort of bipartite graph, then this would be a terrible idea because the one neighborhood in that case is still the full graph. So it's the full set. So the algorithm would be exponential, and there's no hope there. If it's a chain, the algorithm, the one neighborhood is small, but again, why would you bother to use this algorithm when you can just use HMMs and so on? Perhaps one advantage that this algorithm is natively parallel. If you have a grid, then this is linear in the size of the grid, whereas except for the restrictions, the closest that we had before was an algorithm that was exponential. If you have a chimera lattice, how many of you know what a chimera have seen chimera lattices before? Okay, there is a company in Vancouver called D-Wave Systems. They build quantum chips, and what their chips do is they draw samples from these models. But one of their challenges is how to estimate the parameters of these models. Because as their chips been growing over the last few years, and they've been publishing these in Nature, so they have some credibility. As the chip grows, estimating the parameters is a problem that the machine doesn't do. The machine just does the inference with the quantum machine, but it doesn't know how to do the learning. But fortunately for them, we can use this algorithm and convince them. Well, we actually one of my students is working there now, and we're talking about being able to do this to solve that industrial application. And of course, then you get these extremely hard problems in physics, like cubes with frustrated potentials, for which we know that inference is really, really hard, for which we can still do the learning. And for this particular model, here is the comparison of the computational time for a particular precision. This is just showing what the theory says. This model is linear. The junction tree would be exponential in computation.
In many practical applications, like natural language processing or computer vision, we use parameter tying. Does it still work when you tie the parameters of the potentials?
No. I wish it did, but no. We do need to pull off these potentials separately. If we do it, it would be, we could maybe use this intuition to build an approximate algorithm. And that's one of the things that I actually want to be doing over the next year or so, is to try to see, okay, so maybe this algorithm will not always give us the maximal likelihood estimates, but when it gives us different estimates, how good are they? And for Gaussian MRFs, we see that it actually, in terms of relative error, it actually does better than using the junction tree. Now, a lot of people are surprised by this, that you can do better than the exact inference with the junction tree. The problem is that junction tree is not exact always. It requires that triangulation that's NP hard. And so junction tree is, and even if you have the optimal triangulation, then there's still a question of whether the clicks are capture the model class of the clicks of the original model. So there's some subtleties that actually, often people cite junction tree as giving you the exact inference, but it doesn't really always. All right, so very close. Another topic that I'm interested in is deep learning. So this was the state of the art of speech a few years ago, and now it's a lot of cool. You can actually figure out where a restaurant is, provided you don't use Siri. And the pipeline that's been used to do this, at least for the features up to now, is something that, George Dahl, who worked actually with you guys in Redmond, was working on with like Lee Deng and other folks to be able to build the speech recognizers of Microsoft. And it uses a deep net. Now, the kind of work that I've been doing recently with deep nets, and this also work with Misha Daniel, who is the guy that's been doing the random forests, who I'm hoping will be here early next year doing an internship. We've essentially done the following. If you take a receptive field, in a deep net you have these receptive fields for your data, either your speech or images. And if you throw away most of the parameters and you use just a few of the parameters in a predictor, say a Gaussian process predictor, you can actually reconstruct the parameters. So in deep learning, the parameters match the statistics of the world. So a receptive field, which is essentially a neuron in V1, must capture something about images in the world. The whole idea is that if you have 1,000 by 1,000 images, the set of possible images is 256 to the power 1,000,000, and we would never be able to do computer vision if you had to consider the worst case set. So instead, we assume that we're going to match the natural statistics of the world. Now, since the parameters have structure, the basic idea is I don't need all the parameters. We only need a subset, and given that subset, we can predict the rest. So we've implemented this, and we'll be presenting it this year at NIPS, where we actually just use, in some cases, 10% of the parameters in a deep model. And we only do gradient descent on the 10%. And we do that for a range of models, convolutional architectures. Basically, whatever you do using deep learning, this applies. And then we're able to actually predict the remaining parameters. So you actually don't need to keep copies of the full set of parameters. And this for parallel arc, if you have to distribute the parameters of a service as Google does, this actually is a useful trick. What interests me next in doing next with this is that if you have much fewer parameters, that means you, instead of just doing gradients, you can start doing other things like variational Bayes and even HMC. And so I think we finally are coming closer to having Bayesian versions of this, which hopefully in practice will work better. So I'm just not going to go into this in detail. I'm just going to mention what the problem is. So a lot of problems that this is sort of a big area of my research. Some of you were at this workshop a couple of weeks ago and already saw the next part of my talk. So a lot of problems in the world out of this nature. You want to maximize a function, but you don't have access to the function. The function is a black box. So if I want to interact with a user and I'm a program, I don't have a mathematical model of Antonio. So all I can do is ask Antonio a question, probe, and get a reply. And then a lot of parameter tuning, we get grad students to tune the meta parameters of the algorithm until it works well. Essentially, our grad students are the black boxes that are doing the optimization for us. If you want to deploy web pages, massive scale, and do analytics, that is, you want to automatically configure a game or a website to best match what users want or to maximize the revenue for the content providers, then again, you're doing this as in a black box setting. So there's a huge range of problems that are of this nature. I'm not going to go into what we do, but I'm just going to leave you with one image. And this image is this one. And it's based on something that actually Zubin said in a meeting earlier this year. I said we should be thinking like in the world of big data and so on, in trying to get automated statisticians. Sort of something that the automatic statistician, I think that's what you call it. I think I'm calling it the automatic machine learner, same sort of stuff. And so the idea is if you have a toolbox, like in this case that does regression, using a bunch of methods, and you give me a data set, then I would like to automate it. So in this case, this is scikit-learn. I would like to automate scikit-learn so that when you give it a data set, based on the features of the data set, it can automatically decide which method it should try and what the parameters of that method should be. And that, to me, is sort of one of the things for which this sort of black box optimization, where black box optimization can make progress. If you use frequentist techniques here, you get into trouble, because sometimes the number of arms is too large, and frequentist techniques require that you pull each arm, and they're just not applicable. But if you use Bayesian methods, and you can model your problem well, you can actually use your model, correlations and so on in form of a prior to actually do this, to actually get applications that work in practice that allow you to efficiently automate any type of system, whether it's a compiler, whether it's hardware, whether it's your machine learning toolbox, and so on. So with that, I'll end my talk. Thank you.
Thank you very much. Fascinating talk and full of so much material. So I'm sure there will be lots of interesting questions coming up.
Not many. Thanks, Zubin.
Just shy. So I think I know because I've seen this, but maybe you want to tell us what.
Oh yeah, Matt Hoffman is in Cambridge now.
But what's going on in the plot? Because it's quite interesting. Actually.
Oh, okay. So you have several regression functions here in RBF. Is Matt here? No, he's probably in the lab working on a paper. So you have several methods, and for each on this axis over here, So these are, for different colors, mean different types of random forests, different types of linear SVMs, and I think there's kernelized SVMs, and then nearest neighbor regression functions and lasso methods, different types of random forests with different parameters. So each of these guys is one method. And so what we're seeing here is that, so often in practice what you do is you take your data and you do, say, brackets somehow. Say you're doing 5-fold cross-validation and so on. You train in one set of the data and you test on another set of the data. And this all makes sense when your data set is not 1,000,000 points, because cross-validation takes a very long time when you're doing, if you want to consider all possible models and all possible parameter settings of those models, doing cross-validation is really prohibitively expensive. So what this does is it tries to minimize the number of steps you have to do cross-validation. So you would run all the methods initially, but what you hope is that with time, it's picking the models that are the most successful. So even before you have to consider all models in all possible folds, you'll be able to have the winning model. That's essentially what we're after.
So there is a lot of work now in the theoretical computer science community working on bandits with structured arm spaces, right? Where the arms are basically, the arm space is huge, and basically we assume certain structures. And this sort of reminds of the work that was being done on Gaussian processes, where people were looking at what were the sort of correlations between what were the sort of wavelength functions that we should be using for Gaussian processing, right? So isn't the sort of, so the first question is, isn't the problem then just in defining priors over these spaces, which would lead to better sort of probing? And secondly, the second question is, in terms of really interacting with users, what happens is users change over time. The model that you're interacting with is actually dynamic itself, right? So we might be sort of trying to infer what is the latent sort of curve we are sampling from, but then it is changing over time. So do you know of any work which sort of looks at it from the point of modeling dynamics as well of the underlying distribution?
Yeah, there's probably been several works on this. I know Luke Bourne at Harvard has been working. I don't know if I think his paper was rejected, but he's working on this. He has I think a smart idea for doing dynamic Thompson sampling. And Thompson sampling you can do with GP. The GP model, a lot of people use GPs. I've used a lot of GPs. I also did some work actually on dynamic GPs for animation for this type of problem, exactly what you're asking. But GPs are very nice. They're very simple models. I mean, they might be hard to explain to people in the beginning, but once you get them, they're actually super easy to implement. They're very nice. We're working with decision problems, so number of data is not an issue. It's the opposite. It's having too few data that's an issue. But GPs, on the other hand, are just one of the possible models you could use. So at one extreme you're modeling using non-parametric methods with GPs to model the arm structure. But then at the other, but then you could have logistic arms. You could have then at the other extreme beta Bernoulli arms, in which case we're back to the bandits. Yeah. But I think there's a continuous ranging here, and I don't actually see any difference between the bandit problems and what we call typically Bayesian optimization, because it's just a question of changing different models and different utilities. At the end of the day, this is all maximum expected utility. And there's different utilities like Thompson, UCB, expected improvement, and so on. And then there's different models. And it's just a question of mixing and matching them. But the two communities have done different things. And there's been a lot of, nowadays, I think they're converging together. If you're going to NIPS, go to the Bayesian optimization workshop on the second day. But essentially, the other thing that's coming in is all the work on experimental design. Because people are developing things like the knowledge gradient and so on, but that's really just optimal designs so that people had done, like, what's his name? There's a beautiful Bayesian book on the foundations of Bayesian statistics that actually covers this problem as well. And in the theory, we've had a lot of very nice regret bounds for cumulative regret. And for some of these work, we also get bounds that tell us that not only that the cumulative regret vanishes asymptotically, but that you actually get the best arm, that you do the optimization, in other words. The theory still does not reflect the fact that we do better with the Bayesian models. There's a huge gap. So one of the best techniques out there right now is something called Thompson sampling, and it's a heuristic that is almost 100 years old. And there's some theoretical results, but there's this huge gap still between the theory and what we observe in practice. So that's another area that's kind of like random forests with this gap.
There's also the class of racing algorithms. Have you compared against them? Like
yeah, we do much better than those racing algorithms. Yeah, with the Hoofding races and so on. The newer techniques have definitely superseded. We have plenty of, here's essentially a bunch of these methods with you have different utilities. This is the GPUCB with, this is Thompson. Then again, there's all sorts of things that come into the picture, like are you interested in just finding the best arm or minimizing cumulative regret? Or do you have a finite number of arm pools that you're allowed? Or, there's all sorts of constraints under which different models are preferable. In the end, you want to have a good commanding understanding of all of these. But the Hoofding races have been superseded by a lot of techniques. They're no longer competitive.
I think we're a few minutes over time, so we'll stop here. You'll have a chance to meet a lot of us later during lunch and after lunch a little bit until Zubin steals you from us. So thank you again for a fascinating talk.
Thank you.